All right. Hi, I'm Jeremy Faludi, and I'm going to tell you about life cycle assessment, or LCA. And this is going to be in three parts. The first one is, what is LCA for? Second one, what does it measure, what does it not measure? And then last one and the longest one, how to do LCA. And so jumping right in, what is LCA for? Well, it's basically to quantify all the environmental impacts of things. So you look at the whole life cycle of your product or service, or really whatever you want to analyze, and every step of the way, whether it's raw material mining and turning that into finished materials, or manufacturing stages, or transportation, or the use phase, the electricity or water or whatever that the customer uses as part of the life of the product, and the disposal at end of life. All along the way here, there's usually some kind of resource extraction, again, digging stuff out of the ground or farming things, and there's some kind of emissions, whether it be CO2 emissions, particulates, emissions to water, emissions to land, like getting buried in the ground. And life cycle assessment is a way of quantifying all of that. And it is not a perfect science, definitely, but it's one of the best tools that we have. And really the more specific question is, what is your LCA for? Because you can do LCAs at wildly different levels of depth and specificity, and they can be used for different things. And it's important to know at the beginning what you're using it for, because LCA can be an infinitely deep rabbit hole that you dive down, and you need to stop at some point. And so decide at the beginning, what is your LCA for? That'll help you determine how far down this rabbit hole you want to go. For example, you can do quick and simple checking of options. You know, is it better to use ABS plastic or polyethylene plastic? Is it better to use electricity from one source or a different source, etc.? That you can do in a few minutes, very quickly. What we'll mostly be talking about is screening or fast-track LCA, and that can help you figure out what the biggest impacts are in your product. Is the manufacturing stage the most important, or is it the electricity use during the life of the product, for example? Or is it that plastic part, or is it the electronics inside? And you can also establish a baseline, like, here are the total impacts of my product today, or my service today, and how much better can it be? Let's set some goals for improvement next year, 5 years out, etc. And so that can all be done with screening or fast-track LCA. And you can do this in as little as a couple hours sometimes, or a couple days, depending on the complexity of your product. And then the more serious LCAs, things where you're getting an environmental certification, or you want the analysis itself to be ISO 14000 certified, or you're doing an environmental product declaration, an EPD, those require a lot more time and effort. And so that's the sort of thing that can take you 3 months, 6 months, cost $100,000 of labor to do. And these things you can only do at the end of the design phase, when you already know exactly how many grams of every material, how much transportation distance, etc. And then again, you can go infinitely far down the rabbit hole for science. But speaking of when you do LCA, that can be shown here. So again, in the early stages of design, you can't do a very precise LCA because you don't have the data. You haven't decided how many grams of plastic, how many grams of circuit boards, etc. you're going to be using. And so you have to just take more rough ideas, make estimates, get a gut feeling. If you do LCAs more in the sort of narrowing down phase of early design. This is taking the sort of double diamond method of design, where you have a general idea, but you're still working out details. This is the ideal place for streamlined or fast track LCA. And then if you want to do the serious LCA of the like 14,000 or other certifications, again, you'll need to wait until the end of your whole product design cycle when you really know all of the details about things. But of course, you can't use that kind of LCA to make design decisions, because by the time you have enough data to do it, you've already made all of your design decisions. So that's why we're interested in this. And it's not precise. You have to take things with a big grain of salt, but we'll talk about how to manage that. And then the other question is, if you see someone else's LCA, do you trust it? And that's a question of how much data was product specific versus just taking industry average data. Was it prepared by an experienced practitioner, someone who knows what they're doing? And obviously, if it is an ISO 14000 certified analysis, that's much more reliable. But you could still have bad assumptions in there, even though the methodology is good. And there are other people that do certifications of LCAs. But another gold standard is to have it verified by some impartial third party that has criticized the analysis to say, okay, no, you should include this, or you shouldn't count things in that way. And then they go through, redo the analysis, and if the third party accepts it, then it's a more reliable LCA. And just a little more detail on all these things that you might use LCA for. Again, checking options can be super quick, just a few minutes, saying, should we use ABS plastic or PET plastic, something like that? Or should we use injection molding or extrusion, etc.? But then identifying the biggest impacts is a more detailed analysis. And again, this can take a few hours to a few days. And so for an example, for a hairdryer, actually not the one pictured here for customer anonymity, but this is an analysis that I did many years ago. And so I've blanked out the labels on the graph, but this is a graph of the environmental impacts of all the materials and manufacturing of the hairdryer, not the energy use, not the transportation, just the materials and manufacturing. And don't worry for now about the different colors. These are different kinds of environmental impacts all getting added together. We'll talk about that later. But just looking at this graph here, you can see that a lot of things have fairly low impacts, but then there are three things that have really big impacts. They really kind of dominate the impacts here. And what do you think those would be? You know, what do you think this component was in the hairdryer? I actually recommend pausing the video for a second to think about it or discuss with other people, and then start back up again. So this part right here is not the heating wire, the nichrome wire, which is what a lot of people guess. That is a fairly high impact thing, but that's this bar right here. And it's not the motor for the fan. If I remember, that was this here, although actually I'll have to check back because it's been a long time. But no, actually, this bar right here is the ground fault interrupt circuit, which is a little piece of circuitry in a little box on the end of the cord. It's not something that you would even see on the hairdryer itself. It's on the end of the cord. But it's a little safety thing to prevent you from getting electrocuted if you're in the bath with the hairdryer and you drop the hairdryer in the bath. So obviously that's an important thing. You know, we do want safety, but most people would never guess that that was the biggest impact of the hairdryer. And the company here, they had just spent a lot of time and money redesigning their hairdryer to minimize the amount of plastic in the case. And so it came as a bit of a surprise to them to see that, oh yeah, the plastic parts are down here. They're actually kind of irrelevant compared to this one electronic component and a couple of these other other pieces of electrical equipment. And again, if you do this LCA early on, then you can spend your time and money wisely when you're doing the product development process to hit the things that really matter and not waste your time on things that don't matter. But again, this whole thing is just the materials in manufacturing. If you look at that all added up together and compare that to the rest of the life of the hairdryer, so this is transportation from manufacturing in China to sort of an average US location, and then this here is the electricity use during the life of the hairdryer. And obviously, this is way bigger than this. It's not quite a factor of 10 bigger, but it's so much bigger that really you should be spending your design time and money figuring out how to make this hairdryer more energy efficient, because a 10% reduction here is going to make way bigger improvement than even like a 50% reduction here. So again, this is one of the things that LCA is good for, identifying the biggest impacts so you can prioritize your design time and effort. And it's also good for setting baselines and setting goals for improvement. So these are this was a packaging for a different product, a hair straightener, but it was clear PVC blister pack, with some paperboard, pretty standard stuff. But you can see that the impacts are this, but you can do some very quick, easy theoretical scenarios of what would be the improvement if we, let's say, replaced that with paperboard, so cardstock like in a cereal box, or what would be the improvement if you made it out of heavy corrugated cardboard, if you really need protection during shipping. And you can see that just a very quick and simple design change, changing from this PVC blister pack to corrugated cardboard, cuts the impacts by 30 or 40%. And changing it to a paperboard package cuts it by maybe 60%. And so you can see that that goal, saying we want a 60% reduction in impacts in our packaging, that goal is actually really easy and achievable, and you could do it tomorrow. But then some other goals would be much harder to achieve. Okay, so that is basically it for what LCA is for. Now, the next question is, what does LCA measure and not measure? Well, I've got some suggestive things around here, but again, I would suggest taking just a second to pause, think for yourself, or discuss what do you think LCA is likely to include or measure, and what do you think it should measure? So, okay. One thing that I can tell you it doesn't measure any social impacts. It also doesn't measure any financial impacts. It's purely about the environmental impacts of things. But these pictures do represent some of the things that are measured. Like you can count the cumulative energy demand, how much energy is embodied in the product and its manufacturing. That's actually not a great measurement because a kilowatt hour from coal power, it has very different environmental impacts from a kilowatt hour from solar power. And so what we really care about in terms of impacts is things like what are the emissions of carbon dioxide, sulfur dioxide for acidification of waterways and land, and particulate matter, which causes health problems and again causes water and water pollution, and things like that. So we really care not so much about the energy itself, but what are the impacts of producing that energy in terms of air pollution, water pollution, etc. And again, here's just a scene for water pollution. The biggest causes of water pollution are phosphorus and nitrogen for eutrophication. That's where you put too many nutrients in the water and it causes these algae blooms, which then starve out all the other plant life and can hurt animal life as well. And obviously there's resource depletion, digging stuff out of the ground when it's a finite resource. And this is particularly important with critical minerals or critical materials like gold or tantalum for capacitors, indium, other rare elements. But different measurement schemes measure different things. So the IPCC global warming potential, that only measures climate change impacts. It still measures several different things, CO2 obviously, as well as methane, nitrous oxide, CFCs, etc. And it turns those all into CO2 equivalents by normalizing and weighing them. But in the end, it only measures global warming potential. But then there are more comprehensive standards, like Tracy by the US Environmental Protection Agency. It measures a bunch of things. So resource depletion, it measures fossil fuel depletion, because that is, again, a finite resource. Ecosystem health, climate change, acid rain, ecotoxicity, that's things that are not toxic to humans, but are toxic to, say, fish, amphibians, other plants and animals, other organisms. And then eutrophication, I just mentioned, ionizing radiation, ozone depletion in the atmosphere, and habitat destruction. So that's basically land use. And then for human health, there's carcinogens and other toxicity, smog, and particulates. And of course, things that are bad for people are also bad for ecosystems and vice versa. There is some overlap here, but we don't need to get into the details too much. But then the method that I most prefer is actually the recipe method by a company called Prey, which it actually builds on a bunch of different methods of different European systems going back for the past 30 years or so. And as you can see, it measures more things. It also measures mineral depletion, not just fossil fuel depletion. So this system here, it can't tell the difference between mining gold and mining iron, whereas this system can. And it has 2 different measurements for eutrophication, 3 different measurements for ecotoxicity. It's got acidification once again, and 3 different kinds of land use change. And then human health, again, there's the standard sort of carcinogens and other human toxicity here, and then photochemical oxidants, that is basically smog, and particulate matter, climate change, ozone depletion, and ionizing radiation again. And again, like I said before, most of these things should be in both columns. I'm just trying to have the screen not be as busy, but all those things impact both humans and ecosystems. Okay, and where do you get this data? Well, there's a bunch of different databases out there that you just look stuff up in, where you can say, to produce a kilo of steel in a final product, it causes so many kilos of CO2 emissions and sulfur dioxide emissions, and et cetera. You don't have to measure that yourself. That would be impossible, basically. So you just look this stuff up in databases. And the most widely used one is the EcoInvent database. There's various others. And there are also commercial databases that you can pay for that have additional data. And so an analysis that you might get might look like this. This is an analysis that I did of a 3D printer a few years ago, and it's measuring 18 different environmental impact categories. So you can see climate change is measured in kilos of CO2 equivalent, and acidification is measured in kilos of sulfur dioxide equivalents. And you can see there's an absolute number for the sum of the whole life cycle of this particular 3D printer that I was measuring. And then the colors of the bars here are the different life cycle stages that I looked at in this analysis. So that was the manufacturing and materials that went into the 3D printer itself in blue, and then transporting the printer and disposing of the printer at the end of its life. You can see those are very small impacts. And then the electricity use of printing, so that's the yellow, and obviously that's the biggest in most of these categories. Then the material that ended up in the 3D printed part and material that was wasted. And so you look at all these different categories and you say, okay, if I'm trying to, again, it depends on what your LCA is for. You know, if you're trying to use this to make design decisions and finding the biggest impact to set priorities, you can say, oh, well, clearly electricity use is the biggest impact in most of these categories, but it's not the biggest impact in all of the categories. You know, water depletion and mineral depletion, there it's making the printer that are the biggest impacts. And so is this more important than the climate change impacts or the acidification impacts? Yeah, it's hard to say. And you know, we don't expect you to be the environmental scientist with enough expertise to make that judgment. And so there are systems for combining all of these things into a single score. But that requires comparing apples and oranges. You know, a kilo of CO2 emission is totally different from a kilo of mineral depletion or a kilo of water depletion. And so how do you make those decisions of which one is worth more? Well, there's this process of normalizing and weighing all these different impacts. So you get all these different environmental impacts. So again, ozone depletion, climate change, water depletion, etc. And those get translated into how much damage they do to human health. And this is measured in disability-adjusted life years. You know, how likely is a given person to, or an average person, how likely are they to die a year earlier because of a storm from climate change or from drought from climate change? Or if they don't die, maybe they're malnourished, and so that's a disability-adjusted life year. And then secondly, we have the ecosystem damage, and that's measured in percentage of species that are likely to go extinct every year as a result of the climate change and the acidification, et cetera, caused by your product or service. And then finally, there's the cost increase in resources. So, you know, fossil fuels are limited, gold, titanium, other minerals are limited. It's really hard to predict when they're going to run out in the Earth's crust, but it's much easier to say that the cost of mining them out of the ground is going to increase because it's more rare, so you have to make more heroic efforts to dig it out of the ground. So, so you get those three sort of normalized factors, and then the last step is to weigh them of like, this one is a little more important than that one, or maybe all three of them are equally weighted. But then that gives you a final single score that's just in these made-up units of points. And that point doesn't necessarily mean anything by itself, but it's a great way to make relative comparisons between this product and that product, or this design idea and this other design idea. So to illustrate that, here's a comparison of two different buildings that I did life cycle assessments for. An average building in brown and this green building in green. And here are different impact categories that were measured, and you can see that the green building has lower impacts in most of the categories, but not all of them, not for land use or mineral depletion. And so you can say that overall the green building is likely to be better for the environment than the average building, but how much better? And so if you normalize and weigh all this stuff into single units of points, then you can make a pretty quantitative comparison. You can say that yes, this green building had maybe 40% the environmental impacts of the average building. And that is using a methodology called Eco-Indicator 99, which is one of the older ones that the recipe methodology is based on, is an expansion of. But I do have to warn you that these different methodologies for normalizing and weighing, they can come up with very different impacts. And so this is two different analyses for the same product done with the Eco-Indicator 99 methodology and the Tracy methodology. And this one weighs climate change and fossil fuel depletion much more heavily than the Tracy methodology. And so again, some of this has to be up to your judgment and critical thinking, but in general, the eco-indicator and recipe methodologies are more widely used, and I think they're better methodologies for some of the reasons that I mentioned earlier. Recipe in particular measures more stuff, and I think that it has a better weighting scheme. But that is basically it for what LCA measures. So then the final step is, how do you actually do this stuff? So doing LCA is a complicated process, but it's still very manageable. You just break it down into steps. And it does involve spending a lot of time in front of a computer. And I'm going to present it as kind of a linear series of steps, but it's not. It's an iterative process where you go through and redo and rethink things. And we'll talk about that more later. But basically, it's good to know how you do an LCA, even if you never do one, just so that you have a better understanding when you read someone else's LCA or you talk to an LCA practitioner to understand what they're doing and how it works. But basically, it's these steps here. So you first of all set a scope and your boundaries. So the scope is basically, why are you doing this? And that sets the boundaries of what you are going to count and what you're not going to count in your analysis. And then there's the functional unit, which is, how are you going to make fair comparisons? And are you going to say environmental impacts per unit of what? And then the inventory, this is the nuts and bolts where you're actually gathering all the materials and manufacturing data. This is where all the data entry happens. And then you make your computations and you compare the impacts. And then finally, you have a critical thinking step where you look at all the graphs that you got from your computations and you decide, okay, what does this really mean? And again, the scope is based on, why are you doing this LCA? Is this a quick and dirty thing, or is this a super detailed thing that you're going to spend months on? And what's the purpose of it? Is it so that you can find the biggest impacts, so that you can you can set your priorities for green design? Or is it for record keeping or reporting or other things? And again, that determines how far down the rabbit hole you want to go. And then there's the boundaries, what you count and what you don't count. So ideally, you would count the whole life of the product, from raw material extraction and transportation of that to a factory where it gets processed into material, and maybe that has multiple processing stages, gets transported to the user, maybe through a distribution chain, etc. And then the customer uses it, maybe it uses electricity or water or something else, and then more transport to the final end of life, maybe landfill, maybe recycling, etc. And so counting all of that in time is a cradle to grave boundary. But sometimes you don't need to do all of that, particularly if you're doing just a shorter, quicker, more limited LCA to make a very easy decision. You might just do a cradle to gate boundary from raw material extraction to when it leaves the factory, or even just a gate to gate if you're just comparing material A versus material B, or comparing manufacturing method A to manufacturing method B. That would be a gate to gate boundary. And you could also do a gate to grave boundary. Like maybe you're trying to change user behavior through some design intervention that's persuasive design. And so the product itself doesn't change except for the user interface maybe. And you want to see how much of a difference that can make. You might just do the analysis from here to end of life. And so whatever works for your scope, your plan. And then boundaries are not just in time, they're also in space. So a scope 1 boundary is basically just what happens in your factory. A scope 2 boundary also includes the impacts of generating the electricity or other energy that you use in your factories. And then the most complete scope is scope 3, where you're including everything in time and in space. So you're also including the impacts for during the customer use phase and energy or other materials and waste, etc. And just to think about this in a more abstract sense, like why would you choose one boundary versus a different boundary? It's kind of like trying to measure a blade of grass. You know, it's very easy to say the blade of grass is just the green part sticking out of the ground that we can see. You know, this is a very discrete thing. It's easy to see where it starts, where it ends, but that's not the whole picture. Each blade of grass has roots that connect to other blades of grass and the dirt and microorganisms and a whole bunch of other things. And so the more of those things you include, the more complete a picture you'll get of the environmental impacts of your product or service. But also the more of those things you include, the less certain you can be about them. And so you'll just have to figure out what you're okay estimating, what you don't include, and what you think is important to include, even though you're uncertain about it. So then there is the functional unit. How do you make fair comparisons? So if I were doing an LCA of a coffee cup, the environmental impacts required to make this paper cup are way smaller than to make this ceramic mug. You know, there's less material that is extracted, there's a lot less mass, there's less manufacturing. You know, pottery has to be fired in a kiln, that's very energy intensive. So if you were just saying what are the environmental impacts of producing one coffee cup, then this would be the more environmentally friendly option, right? But I think nobody would say that that is the more eco-friendly choice here, right? And that's because that's not a fair comparison, because it's not the function of a coffee cup. The function of a coffee cup is to drink coffee out of. And so something where you can drink 500, 1,000, 2,000 cups of coffee out of this cup, and you can only drink maybe 1 or 2 out of this cup, that is a better unit of comparison. And so that's the functional unit that we want here. And so instead of looking at the environmental impacts per cup produced, you want to look at the environmental impacts per cup of coffee drunk. Maybe. So that would be a decent functional unit here. But actually, that's even not necessarily the perfect unit, because this cup is maybe twice as big as this cup. So you get twice as much coffee per cup here. So if you really want to make a fair comparison, you want to go by something like per serving of coffee. So let's say that's per 250 milliliters or 8.5 ounces of coffee drunk. And then you can say, okay, here were all the environmental impacts of making this cup, and so we get one of those per serving of coffee. But then the environmental impacts here, this cup maybe lasts for 5 years, and maybe you drink 2 cups of coffee a day out of it. And so maybe this, the environmental impacts of producing this get divided by a factor of whatever, 2,000, 4,000, something like that. And that's how you can tell that this is a more environmentally friendly choice than this. But what would be a functional unit for comparing, let's say, steel columns in a building versus stone columns? Again, doing environmental impacts per kilo of material wouldn't make any sense, because stone is a lot heavier than steel. But what would be a fair functional unit? And I would suggest pausing the video for a minute, maybe discussing it with people if you can, and think about what you think would be a good functional unit there. Okay, so what most people do in a situation like this is they count the environmental impacts per kilo of load-bearing capacity over, let's say, a 50-year lifespan, whatever you think the life of your building is going to be. And then that would provide a more fair comparison here. Or if you want to compare a normal gas-powered car versus a hybrid car versus an electric car versus a bus or a train or something else, or a bicycle, what would be an appropriate functional unit there? Again, pause, think about it. What most people do here is environmental impacts per passenger mile or per passenger kilometer, because that way you can make a fair comparison between the bus, which carries a whole lot of people, versus a car where there's often just one person. Or what about for cell phones? The unit that most people will use here is per hour of use. That's a pretty standard one for lots of electronics, laptops, wearable devices, and just other things where it's the interaction time that matters. Okay, so once you've got your scope boundaries functional unit, then you actually get into the nitty-gritty of what are all the materials? How many grams of ABS plastic do I have? How many grams of PET plastic do I have? What were the manufacturing methods? Was this injection molded? Like this cable here, it was copper, and the manufacturing method for copper was drawing into wire. And the plastic sheathing, that was extruded, et cetera, et cetera. And you add up all that stuff and the transportation, how far did it come? How far was it shipped by boat, by rail, by truck? And what's the energy use during the lifetime? And is that energy, let's say, electricity from the Netherlands electrical grid or US electrical grid, et cetera? And what happens at end of life? And this sounds very straightforward, but actually it's very time consuming. Most bill of materials that you get from companies don't have a lot of this data, and so you have to take your best guess. And then even when you do have perfect data, because you're the one designing it, you still often have to use proxies. And that's because some of this stuff is not in the databases that you're looking for it in. So for example, this material here from this hair straightener, that was little sheets of mica to be fireproof for heating. And so that's a nice simple mineral, but it's not in the database. And so I had to substitute that for something that I thought would be a good proxy environmentally, not necessarily functionally, but environmentally. What's a similar thing, a similar mineral that has similar non-toxicity and similar abundance in the world and similar sort of mining procedures. Doesn't take a whole lot to mine. And so I chose gypsum as a simple substitution for mica. But you could also add up components as well. So let's say this whole length of wire, you might say, okay, that is composed out of a certain amount of copper with a manufacturing method of being drawn into wire, and it's also a certain amount of plastic with a manufacturing method of extrusion. And you can even do this for chemical processes or whatever extra energy you think is needed to, let's say, bake materials or do whatever processing you need. So, so these are two ways of handling things that are not already in the database, which will always happen to you. But then once you've done the inventory, you can compute the impacts, and you can actually do this on paper, with pen, with lookup tables, and just doing the math yourself. But it's usually easier to use at least a spreadsheet to do the math for you. And there's tons of LCA software out there that makes your life easier and graphs things for you and whatnot. So the most basic, I would say, there's this Ocala guide, which is a physical paper publication with physical paper tables that you can look stuff up in. So you can say, okay, I've got 2 pounds of ABS plastic. So you look through the list here, okay, ABS, and the impacts in Ocala millipoints, that's their methodology, the impacts in Ocala millipoints per pound is 47, and so I've got 2 pounds of that ABS material, so it's 47 times 2. Okay, so those are the impacts for the material. And then what was the manufacturing method? Probably injection molding. So you look down, okay, polymer forming, okay, injection molding. Okay, so 11. And again, there's 2 pounds of it, so 11 times 2. And you just add all of that up for your whole product. But again, you'll want to look for material or process equivalents or proxies because, as you can see, this is a pretty limited database to draw from. You know, if I have, let's say, PLA plastic, that's not in this list. So I would have to make an estimate of what I think it's closest to. And again, there are lots of different kinds of software. The ones that are most frequently used by professionals doing serious, like 3 to 6 month LCAs that are ISO certified and all that are SEMA Pro and Gabi. And then they're easier, cheaper, web-based ones like Sustainable Minds is the one that I usually recommend to people that are just learning LCA because it's got a nice simple user interface. But actually Equalizer is a free one that also has a very good interface as well. And some LCA software is actually built into CAD programs. So SolidWorks has a sustainability plugin where you just build your model in CAD and you assign the materials, and then you can click a button and it will do the analysis for you. And this is what the user interface looks like for most LCA software. It's not exactly the most user-friendly, and that's why I recommend things like Sustainable Minds or Equalizer, or this is a screenshot of the results that the SolidWorks Sustainability Express plugin gives you. And again, you just do your CAD modeling like you normally would, and you click a button, and it can tell you the impacts of things. But okay, so all this LCA software or you doing things in a spreadsheet and making the graphs yourself, what does this all mean? And again, this gets back to why are you doing LCA? What's the point of this? And for our purposes here, we're talking about early design phase and where we're looking for the biggest environmental impacts of things. And so how do you make sense of this? You can see a graph like this. This was, again, an LCA that I did of a 3D printer. And you can say, okay, so energy use was the biggest environmental impact here, and then the production of the machine itself was also significant. The materials used in the actual 3D printing were not significant. But you can see there are these error bars here, and it's very important to think about the error bars. That is your uncertainty and your sensitivity to initial conditions. Sometimes it matters a whole lot whether you made the right guess about where you were going to land. And sometimes it doesn't matter at all. So in the case of this graph here, in this particular scenario that I was looking at, the impacts for materials and material waste are so small that it doesn't matter how accurate those were. I could have been off by a factor of 10 in my measurements there, or estimations, and it wouldn't matter to the purpose that I'm using this LCA for, which is to identify the biggest impacts to set design priorities. And again, you might have a different purpose for your LCA. But some other uncertainties might be bigger. For example, here is an LCA of a bunch of different 3D printers and comparing them to CNC mills. And so if I were going to say, is it environmentally better for me to CNC mill this complicated part or to 3D print it out of the same material, out of ABS plastic, let's say, then I would look at the uncertainties here, and here the blurs are how I'm representing uncertainty rather than error bars. But I could say, well, there's a lot of uncertainty here, and if I'm comparing it against this particular 3D printer, there's a lot of uncertainty here as well, and so I don't actually know which one is better. I can't really make a decision about whether I should CNC mill it or 3D print it with these two machines here. But I could say, well, if I 3D print it from this machine over here, that definitely has a much lower impact. And it doesn't matter that there's a really big uncertainty here and here. And so again, this is about what you're using your LCAs for, and in the early stages of design, there will be lots of uncertainty, but that doesn't mean you just have to throw up your hands and walk away and give up. You can still make decisions in the midst of a lot of uncertainty. And so then sensitivity analysis is not just a matter of how certain you are of your data. And actually, I should say that even the best data that you ever have, you'll never be better than plus or minus 10% uncertainty with anything. Because you're looking stuff up in a database, you didn't actually measure the kilos of CO2 emissions yourself, all that. So a bare minimum with the best data is plus or minus 10% uncertainty. And you can often be plus or minus 30%, 50%, 100%, even 500% if you're totally just taking a huge wild guess. But again, even with large uncertainties, you can often make intelligent decisions. But then there's sensitivity analysis, which is, what if you're wrong about the assumptions that you're making? You're not sure what your design is going to be yet. And so what if it uses, let's say, what if it uses aluminum instead of steel? Or what if it uses 5 kilos of aluminum rather than 1 kilo of aluminum? So you can run different scenarios and see how much it changes your results. So this is that same graph from earlier of the hairdryer, comparing the manufacturing impacts to transport to the use phase. And energy really dominated here, but this was assuming that the user would use that hairdryer for 10 minutes a day, every day for 5 years. And I thought, that's kind of a lot. I mean, maybe it's totally accurate. I don't know their customers, but so I ran another scenario of like, well, what if your customer only uses it for 2 minutes a day for 5 years? And then, as you can see, the energy use comes way down compared to manufacturing and transport. And so it's a different situation now design-wise, where here you really kind of don't care what's happening manufacturing-wise, because even a 10% reduction in energy use, like I said before, would make a much bigger difference than even a 50% reduction in the manufacturing impacts. So you should really spend all of your time and attention design-wise on making it more energy efficient. But if that's not how it's used, then, and the energy use is much smaller, then yeah, it is probably worth your time to actually look at how you could make the materials in manufacturing better also. And so this gets into scenario modeling of what do you think the different scenarios are that are possibilities? And does it depend on user behavior? Does it depend on, let's say, what country you're shipping to, so they have different electricity mixes? You know, some places have much more eco-friendly electricity grids than others. Or are there some other kinds of scenarios? So this is that same 3D printer that I analyzed earlier, but actually the scenario that I was modeling here was a really stupid scenario where they're only printing 1 part per week and they're leaving the machine running the rest of the time. And yes, that is how some people use 3D printers, but it's really not ideal. And so if you're really using that printer 24 hours a day, 7 days a week, and you're really maximizing the utilization of it, then first of all, the total impacts are way smaller. They're like a factor of 10 smaller here. And you can see that for some scenarios, like if you're only printing 1 part per week, but you at least turn the machine off when you're not using it, then the ratio of what the biggest impacts are changes as well. So here, it's no longer the energy use during printing that is the biggest environmental impact. It's the production of the printer itself. And so then you can say, okay, well, what's my green redesign priority here? Is it to make this machine more easily shareable so that more people can use it and we can increase the utilization, for example? But again, that's based on what you're using your LCA for, what the purpose of your LCA is. And just a reminder once again that you can have lots of different scenarios, and you can even have different uncertainties in different scenarios. You know, there's a lot of uncertainty in this scenario. This scenario is much more tightly defined, and you can still make intelligent decisions when there's a lot of uncertainty and when there are very different ways of using your product or scenarios in which that change its impacts. So, okay, and that's the interpretation of what you're doing. And again, this is not a cookbook thing. You have to exercise critical thinking to decide these things. And then there's communicating your results to other people. How do you make it simple to understand and get the point across that you are trying to make? And so is a graph like this the best kind of thing? Or could this be misleading? Because, for example, I mentioned that all this stuff was the plastic components of the hairdryer, but what if you added all of these up? What if you stacked up all of the plastic parts together? Would they end up being as big an impact as that one piece of electronics? So maybe that would change whether you thought it was worth your time to redesign the plastic parts or not. And again, that's a data visualization and communication thing. Or this is just another way of visualizing data. So here the different colors are not different kinds of environmental impacts like they were here. Here, this is all single score impacts, and the different colors are the different parts of the product or its life cycle. So like electricity use is the dark blue, and then steel, copper, etc. And then this adds up all of the life cycle impacts of one product or design idea so that you can very easily compare it to another product or design idea. And that, it's just an easier way to make decisions. Or you can use Sankey diagrams, which are more of a flow chart. This is the same data as before for the hairdryer, but it's showing you like the different manufacturing stages and the transportation from China and the electricity use during life. And the thickness of the arrow is showing you that the electricity during life is the biggest impact. And again, this is the same graph from before, and I like showing uncertainty as blurs because it's a nice intuitive way for even non-technical people to get that we don't know exactly what the result was here, but we do know with much greater precision what the result was here. And yeah, even for technical people, honestly, a lot of people, they see the error bars, but they ignore them. And so this is a way of forcing people to acknowledge uncertainty. And again, throughout your whole LCA, it's good to have an external review of the process, not just the communication and interpretation, but also the scope and boundary setting and the inventory and all that. And as I mentioned earlier, this isn't a linear process. I presented that way for simplicity, but it's really a very iterative process. So you start out setting your goal and scope, but maybe in the process of doing your inventory analysis, you discover, oh, actually there's this thing that wasn't in our original scope, but it would have a huge environmental impact, and so we really should think about that. So you go back and revise your scope, or once you do the impact assessment, you get the results of things, you find, oh, maybe these things don't matter, and so let's leave them out of the scope, etc. And again, it's all about what is the purpose of your LCA, and then your interpretation can change things as well. You might you might have been analyzing coffee cups, and you might have started out doing your inventory and impact assessment just by environmental impacts per cup produced, and then you look at the results and say, oh no, that's stupid, we should change the functional unit, and then that will cause you to redo your calculations here as well. But yeah, so if you need to go back and redo things, that's not a problem. That's in fact good. You're exercising critical thinking and doing the process correctly. But yeah, so that is basically it about how to do life cycle assessment. And if you want more of a step-by-step example, I do have another video that uses a simple lookup table with Excel spreadsheet, and that's really doing the calculations really step-by-step so that you can see every bit. Because again, this stuff is pretty complicated overall, but if you break it down into the individual steps, it's really quite manageable. So there you go. Thanks for watching.